Namaste, welcome to Pythagoras Academy. This is Vikram Dachepally. In this video, I am going to discuss a very challenging concept, that is the concept of oblique collision. Look at this example where M1 and M2 moving in different directions with speeds U1 and U2 collide with each other on their path, and in the process of collision they exchange their linear momentum and energy. So what happens next after this collision is dealing with oblique collision. The entire process of dealing with oblique collision, I have made it simple by splitting into 4 steps. So let us follow these 4 steps to deal with any problem of oblique collision. Step 1. Figure out the line of collision. When two bodies collide, there is one direction or one line along which the collisive forces act. That line along which the collisive forces are acting is known as line of collision, or line of impulse, or line of impact. There are 3 names to that line. Let us call that as line of collision in this discussion. So when M1 and M2 hit each other at this point, it is very clear that they exert normal contact force on each other. So this yellow line, as you see, will be the line of collision. Because M1 applies force on M2 along this direction, M2 applies force on M1 in this direction. So this yellow line is the line along which the collisive forces are acting. So this is a line of collision in this case. So this is step 1, figuring out or identifying the line of collision. Then comes step 2, resolve velocities along and perpendicular to line of collision. As you can clearly see that the velocity of M1 and M2 are inclined at some angle with line of collision. This is the very reason why this collision is known as oblique collision. If the velocities are along the line of collision, that is known as head-on collision. So the second step is to resolve the velocities. So let us do that. Say U1 is making some angle θ1 with line of collision. So there is a component of velocity along the line of collision, that is U1 cos θ1, or I'll simply write it as U1x. And there is a component of velocity perpendicular to line of impact or line of collision. So I'll name it as U1y, which is U1 sin θ1. Similarly, U2 is making angle θ2, some angle with line of collision. So I can resolve U2. Along the line of collision, it is U2x, and perpendicular to line of collision, it is U2y. This is the second step. Third step, apply the concept of head-on collision along the line of impact. So what we got is, this is U1x and U2x. These are the components of velocities along the line of collision. So third step is to apply the concept of head-on collision along the line of collision. As far as the concept of head-on collision is concerned, we do not bother about the perpendicular components. All we need is this U1x and U2x. So by conservation of linear momentum, this is the first step. By conservation of linear momentum, initial momentum, I'll take the line of collision as x-axis. So this is the positive direction. The direction of U1x, I'll take it as positive. So initial momentum of M1 is M1 into U1x along the line of collision, and minus M2 into U2x, because the direction of U2x is opposite to U1x. That is equal to, let me say finally, M1 gets velocity V1 after collision, M2 gets velocity V2. We are supposed to find V1 and V2 in step 3. So final momentum of the system, that is M1 V1 plus M2 V2. This is the first equation. The second equation is by Newton's law of restitution. By Newton's law of restitution, velocity of separation after collision, that is V2 minus V1, is equal to E times coefficient of restitution of the two bodies times velocity of approach. Velocity of approach would be U1x minus U2x, but U2x has got opposite direction, so minus U2x. So this turns out to be V2 minus V1, that is equal to E times U1x plus U2x in this case. Depending on the problem that you're dealing with, there can be difference in this plus and minus signs. All I'm taking is, I've taken this direction to be positive, so obviously the opposite direction is negative. So by these two equations, we have two unknowns v1 and v2. Those are the velocity components after collision, and we have two equations to solve them, one by conservation of linear momentum, the other one is by Newton's law of restitution. I have explained this in another video, the concept of head-on collision. I'll give the link of that video in the description, you may check that out. Anyhow, in step 3, what we can find is v1 and v2. But it is not yet over. There is one last important step, that is step 4. Velocity components perpendicular to line of impact or line of collision do not change. Before collision, this is the situation. After collision, so there is u1y and u2y which we resolved in step 2. These are unaffected. Because the collisive force is along line of impact, only the components along the line of impact are affected. The components of velocities perpendicular to this line of impact or collision remains unchanged. So you should not forget that. So we found v1 and v2, these components in step 3. So if we get v2 negative, then the direction is opposite. So positive and negative signs will tell us the exact directions of v1 and v2 after collision, depending on the problem. So this is the final situation. After collision, the bodies get separated along the line of collision. The resultant velocity of m1 is in this direction. The resultant velocity of m2 is this. So this is m1 and m2. The speed of or the magnitude of velocity of m1 after collision would be root over v1 square plus unchanged component, that is u1y whole square. The speed of m2 after collision would be v2 square plus u2y whole square under root, as you can see in the figure. So this is the situation after collision. So these are the 4 steps which are very much useful, and you can solve any problem of oblique collision in a very easy way. If you have any questions or suggestions, you can always use the comment section to interact with me. I'll be more than happy to respond and answer your questions. This is Vikram Dachepally signing off. Namaste.